Okay, so today we're going to be looking at solving the second order differential equations that we looked on Tuesday, but now we're going to solve it using the Laplace transform. Okay, now this exact method won't be tested, so I won't say use the Laplace transform to solve it. I'll just give you the differential equation, and then you can decide on the method. Right, so you can use the method that we covered on Tuesday. You can use this method. If you know a different method, you can use that one as well. I'll leave it up to you. Okay. And as always, if you can do things multiple ways, you get the marks for both. Okay. So let's do a quick recap of the Laplace transform. So given a function little f of t, usually a function of time, we convert it to a function of frequency given by capital F of S, and we calculate that using this integral transform. Okay, improper integral there. Okay, from this integral definition, we get a number of properties. We did go through this before, but I'll list them out again. And then two very important properties, the Laplace transform of the derivative and the Laplace transform of the second derivative. Okay, you need to make notes of that. It will not be given to you. Okay, so let's just list these out. Okay, so the first property is linearity. So if we have the Laplace transform of A times f of t plus b times g of t, then the constants can come out and we can do the Laplace transform of each of them individually. So this will be A f of s plus b g of s. Okay. So we can separate it with the sum. Okay, then the second property, the Laplace transform of t to the n. Okay, so t to the 0, t to the 1, t squared, t cubed, all of those. This is equal to n factorial over s to the n plus 1. Okay, we showed this before. Okay, and then the two important ones, so put a little star for these. The Laplace transform of f prime. Okay, I think this was one of the homework problems. You do integration by parts, and we can show that this is equal to s times f of s minus f at 0. Okay, and then the other one that we're going to need, the Laplace transform of f double prime. Again, you can just use integration by parts, but here, because it's the second derivative, you have to do it twice. Okay, but same idea as the first one there. So this is going to be equal to s squared f of s minus s times f at 0 minus f prime at 0. Then a few more. Again, we covered this last time, but I'll just list them out. We'll need them for today. The Laplace transform of e to the minus alpha t. This is 1 over s plus alpha. The Laplace transform for sine omega t. This is going to be omega over s squared plus omega squared. The Laplace transform for cos omega t. Very similar to the one for sine, but there's an s at the top. Okay, so sine, that comes with the omega at the top, and then the cos, that comes with the s at the top. Okay, and then the last two we need for today, Laplace transform e to the minus alpha t sine omega t. I think this one was in the tutorial. You can check for that. Okay, this is going to be omega over, very similar to the one for sine, but because of this exponential, it's going to be s plus alpha. Okay, so sine just has the omega at the top and s at the bottom, but if you put that exponential in front, then it becomes s plus alpha. Okay, and then the last one, we'll need e to the minus alpha t cos omega t. Okay, same as the cos one from before, but instead of s, it's s plus alpha. So these are just a few that we looked at last time. We'll need them for today. But if you in any doubts on, the Laplace transform of any function, you can always go back to the definition here. Yeah. But for tests and exams and so on, I'm not going to expect you to go back to the definition every time. So here, if you need the Laplace transform of t squared, you can just write the answer down. Okay, you don't need to show the full working for that. Okay, so let's go through the general method of solving these, and then we'll look at an example. So let's say we have a second order linear differential equation with constant coefficients, like we had on Tuesday. So it might be something like this. AY double prime plus BY prime plus CY equals sum f of t. Here we're going to write it in terms of t, because as you'll see this later on with the electrical engineering, these will be functions of time. Okay. So we'll use time as well here just to show that. Okay, so this will be a function of time. Then when you do the Laplace transform, it becomes a function of frequency, and you use that for your signal processing and things like that. But for our case, we just want to solve the equation. Okay, so we have our differential equation. We also need two initial conditions. So we need two initial conditions. Let's say y of 0 and y prime of 0. Okay. So remember, together the differential equation and the two initial conditions, that becomes an initial value problem. Okay. So we're going to be using the Laplace transform to solve this initial value problem. Okay, to solve the initial value, given by that. So I'm going to show the steps for any equation like this, and then we'll look at a particular example. Okay, so step one is to apply the Laplace transform on both sides of the equation. So we're going to do that. So Laplace transform on the left side and on the right side. So we have something like that. Now we know that the Laplace transform is linear. So this left-hand side here, we can split up into individual terms, and those constants can just come out. Now this only works if it has constant coefficients. Okay, so later on, when you look at non-constant coefficients, for example, x times y double prime, that x can't jump out. Okay, so you need to do another method for that. Okay, but here we can take all the constants out. So it will be a Laplace transform of y double prime plus b Laplace transform of y prime plus c Laplace transform of y, and on the other side, Laplace transform of f. Okay, so we have something like that. Now, for each of these terms with the Laplace transform, we're going to use the properties that we looked at a bit earlier. So for the first one, this is the second derivative. So if we go back here, there. So just replace the f with y. So Laplace transform of the second derivative, we're going to write that out. And then the Laplace transform for y prime, we're going to use this first one. Okay, and then write it out. Okay, so we have A. Again, the y double prime, we can look back here. That's going to be all of this here. But instead of F, we can call it capital Y. Okay, so all of that in brackets is from that first term, okay, using the property. Plus B, and then we can do the same thing with the second term. Okay, so it's going to look like that. And then finally, C times the Laplace transform of Y, but we said that's going to be capital Y. Yeah. And on the right side, whatever that function is, let's call that capital F of S. Yeah. So we did the Laplace transform throughout, and notice that there are no more derivatives. Yeah. So once we do the Laplace transform, this just becomes an algebraic equation for capital Y. All the derivatives are now gone. Yeah. So all the derivatives are gone. For step 2, we can now solve for this capital Y. Yeah. So we see that that Y of S appears all on that left-hand side. We can do some grouping to put all of the Y terms together. Everything else we're going to take to the other side. Okay, so the first term, A S squared Y, we'll put that down. Okay. And then the next terms there, those have nothing to do with the capital Y. We're going to take that to the other side. From the second bracket, we have BS times Y. We're going to keep that. And then the last one there, C times Y, we're going to keep that. Okay, and all the other stuff we take over to the right-hand side. So we already have this capital F of S, so we're going to keep that there. Then the minus A S Y naught, take that over. Then we have a minus A Y prime naught, we're going to take that over. Okay. And lastly, for the second bracket, we've got minus B Y naught, we're going to take that over. So anything with the capital Y, we leave that on the left side. Everything else, that is going to go on the right side. Now, each of these terms have a capital Y, so we're going to factor that out. And that quadratic there is left over. And on the other side, we're just going to leave that as is. So we end up with this. Now we want to get this Y of S by itself, so we're going to divide through by that quadratic. Okay, so this right side we'll just leave as is, and then divide through by that. Yeah, and we end up with this mess on the right side. Now, remember what this capital Y of S was. That was the Laplace transform of Y of t. So if capital Y of S is the Laplace transform of Y of t, we can use the inverse Laplace transform, going backwards, to get Y of t. So that will be step 3. To get Y of t. Okay, so we're going to undo that Laplace transform, which is basically looking at this here. So maybe we get something like this on the right-hand side. Okay, so we end up with something like that. Then the inverse Laplace transform will just be cos. We just look at it going backwards. Or for example, if we have 1 over s squared over there, that means n is 2. N is 1 there, 1 over s squared. If we go backwards, it's just t. Okay, so for the inverse Laplace transform, you're just looking at this going backwards. Okay, but we'll look at the example in a bit. Okay, so we use the inverse Laplace transform to get Y of t. Okay, and that's just looking back at the table. So we'll have individual terms. We look at the table and we'll say, okay, this term goes to cos, this term goes to t squared, this term goes to e to the t, something like that. And then we can write out the answer. Okay, so these are the 3 steps that we're going to be following. Okay, and again, the electrical engineers, you're going to be using this a whole lot when you do your signal processing. Any questions on the 3 steps before we get to the example? All good. Okay, so step 1, apply Laplace transform to both sides. Step 2, solve for the capital Y of S. Step 3, use your table to find the inverse. Okay, 3 steps. So let's have a look at an example. Okay, so we need some initial value problem. Let's say we have the following IVP. So y double prime minus 4y prime plus 5y. Again, constant coefficients. We won't be dealing with anything else. Is equal to 1 plus t. Yeah, so that gives us our equation. We know how to solve it from Tuesday. So now we're going to solve it using the Laplace transform. And then you can check. So homework, try it the other way, see if you get the same thing. And then the 2 initial conditions, let's say y of 0 is 0, y prime of 0 is also 0. Makes it a little bit easier. Okay. So let's go through the steps. Step 1, Laplace transform of both sides. Okay, so I'll just put there L, so apply L to both sides. Okay, so we have y double prime minus 4y prime plus 5y. And then on the right side, 1 plus t. Okay. Now on the left side, we can split that up into 3 terms. So we're going to have the Laplace transform of y double prime. The 4, that's a constant, that can come out. And the 5, that's a constant, that can come out. Okay, and then on the right side, we can split that up as well. Okay, so we get 1 and t. Now for each of those terms on the left there, we're going to use that property So for the first one, we use the property for the second derivative. The second one is the property for the first derivative. And the third one is just capital Y, right? There's nothing more to do there. Okay. So this first one, this was s squared capital Y minus sy at 0 minus y prime at 0. Okay, it's always the same there. Okay, then minus 4, and then we're going to use the first derivative property. So that was s capital Y minus y at 0. Okay, that's for the second bracket. And then the last one, the Laplace transform of y, we're just going to call that capital Y. Okay. And then we need to do this right-hand side. So we have the Laplace transform of 1 and t. Now this 1 over here, I'm going to write that as t to the 0. Okay, so that we can use this property over here. Okay, so t to the 0, that's just going to be 1, which is what we want. So n will be 0. The top will just be a 1. The bottom will be s. So we get 1 over s. Okay. And then the next one, t, that has exponent 1. So we go back here. Okay, so t to the 1. So we get 1 factorial, that's going to be 1. And then the bottom will be s squared. Okay. Any questions so far? Yeah, so we just did L on both sides and then used that table of properties to get that last line. Okay, step 2, we need to solve for that capital Y. There's some simplifying we can do first. We see these initial conditions over here. Okay, y of 0, y prime of 0. In the question, we know that they're both 0. So we can cross them out. So that's going to be 0, that's going to be 0, that's going to be 0. Okay, so at this stage, you can substitute your initial conditions. In this case, they're both 0. Okay, step 2. Okay, step 2, solve for the capital Y. So each of these brackets here has a capital Y. We want to keep that on the left side. Anything else we want to take over to the right side. Okay, so let's just rewrite this a bit neatly. So we have s squared y. The other terms go away. Then we have minus 4sy and plus 5y. Okay, so that's just simplifying that left side. Now there's no constants or anything to take over to the other side, so we just leave it like that. Okay, then on the right side, we have 1 over s and 1 over s squared. Okay. Now back to the left side, we've got 3 terms with y. We can factor that out. Okay, and this other side, we can keep that. Yeah. And then finally, to solve for y of s, we can divide through by that quadratic. So we just divide both of those fractions by that quadratic there. And now we have capital Y of s. Okay, so step 2, done. And finally, for step 3, we're going to apply the inverse Laplace transform, which just means look at the table, see what it should be on both sides here. So we're going to apply L inverse on both sides. So on the left side, when we apply the inverse, we're going to go from capital Y of S back to the little y of t. Okay, and on the right side, we need to do this inverse for both of those fractions. Okay. Now we check these terms on the right side. If they appear in the table, then we can just write down the answer. If they don't appear in the table, then we have to do a little bit more work. Okay, so let's have a look. So we've got 1 over s times s squared minus 4s plus 5. Let's check the table. Okay, so here we've got the quadratic here for sine and cosine, but there's no s in front. Okay, so check here. We've got s times a quadratic and s squared times a quadratic. Over here, it's just the quadratic. Okay, which means we need to split that fraction into 2 parts. Okay, one fraction for the s squared and the other one for the quadratic part. Okay, and then the same for the first one. We're going to split that into 2 fractions, one with the s and one with the quadratic. So split the fraction into 2 parts. So we're going to have something with the 1 over s as the one fraction and 1 over the quadratic as the other fraction. Okay. And then the same thing for the second fraction. The s squared we're going to make into one fraction and the quadratic into another fraction. So that will be 1 over s squared and s squared minus 4s plus 5. Okay. How do we split fractions like that? What's the method called? If I got a fraction with some products in the bottom and I want to split them up, what's that method called? Sleepy today. Partial fraction decomposition. Remember that. Yeah. Remember partial fraction decomposition from last semester. If we have some fraction with a product in the bottom, you know, the linear times a quadratic or linear times a linear, and we want to split it up, we need partial fraction decomposition. So we're going to do that for these 2 fractions here. Okay, so we need to apply this partial fraction decomposition. To the 2 fractions. So it will be something over s and something over s squared minus 4s plus 5. Okay, so let's do this first one here. 1 over s and then this s squared minus 4s plus 5. Yep. So first step, check if we can factor that quadratic. Right? If we can factor it, then we write it as the 2 linear terms. If we can't factor it, then it's an irreducible quadratic, and we have to do that case 2. Okay, so s squared minus 4s plus 5, can that be factored into 2 terms? No. Okay, so that's going to be an irreducible quadratic. So we're going to have A over S for the first one, and then BS plus C over the quadratic for the second one. Right, because it's S linear, so there's just a A at the top. And then that's an irreducible quadratic, so it will be BS plus C over the quadratic. Okay, same as we did before. So that's for the first fraction, and we're going to do the same thing for the second one here with the S squared. Okay, same idea. Now this one is repeated. It's S squared. So we're going to have A over S, B over S squared for the repeating, and then CS plus D for the quadratic. So A over S, but it's repeated because of the S squared, so we need another one. And then the quadratic parts as before. Okay. So we've done the partial fractions decomposition now. All right. Any questions so far? Oh, good. Okay. Please do not forget the partial fraction decomposition. Okay. So we won't go through the whole calculation on finding A, B, and C and all of that. You know how to do that. Cross multiply, solve the simultaneous equations. Okay. So homework. Solve for the coefficients. Okay, you know how to do that. Cross multiply the fractions there, and then solve the simultaneous equations. So homework, please go through that. I'll just give you the answers and then you can check. So once we've done solving for the coefficients there, we'll end up with the following. So here you can check. So this y of s from here, this will be equal to, sorry, not y of s, log y of t. Is the inverse Laplace transform of the fractions that we just split up. And those coefficients will be 9 over 25, 1 over s. So that was the a value, plus 1 over 5, 1 over s squared. So that was with the b. Yeah. And then the others are given by minus 9 over 25, s over s squared, minus 4s plus 5, and 31 over 25, 1 over s squared minus 4s plus 5. Yeah, so that's after splitting it up. Now what we want to do is look at this term by term and try and match it to something from the table. So these first two are very easy to do. So 1 over s and 1 over s squared. We go back to our table. That's just the second row here. Okay, so 1 over s, that means n will be 0. So that will become 1. And then the 1 over s squared, for that second term we had, that's when n is 1. So that will become t. And you just look at the table and you can go over that. So this one, that will become 1. And this one, that will become t. You just look at the table and write it down. But now these ones are a little bit more tricky. we've got this quadratic in the bottom here for both of them. And over here, let's go back. Okay, there's the ones with the quadratic in the bottom. Okay, you see that it's going to be s squared or s plus alpha squared for those. Okay, over here, we've got s squared minus 4s. That doesn't work. So what do we need to do to get this to look more like what we had in the table? Okay, remember back to when we did the partial fractions? If you have something like that in your denominator and you want to integrate it, what do you do? Oh, someone said it? Complete the square. Exactly. Right, it's the same steps as what we did when we did the integration. Okay, if you have some quadratic in the bottom, you want to integrate it, you complete the square. Same thing happens here. Okay, everyone familiar with completing the square from last time? Okay, so it's going to be s minus half of the 4 squared plus the 4 plus 5. Okay, so we complete the square, and we end up with the following. Okay, so y of t, that's going to be the inverse Laplace transform. Okay, so I'll just rewrite it and then put the completing the square in. So that will be 9 over 25, 1 over s, plus 1 over 5, 1 over s, minus 9 over 25, s over, and then when we complete the square, it will be s minus 2 squared, so we can get the 4 there, plus 1. Okay, you can check that quite easily. So s squared minus 4s plus 4 plus the 1, that gives us the plus 5. Okay, so that's fine. And then the last one, plus 31 over 25, same thing, s minus 2 squared plus 1. Okay, now that we've completed the square for both of them, we go back to the table, and we see it looks like those last two. Okay, does everyone see that? We completed the square, and we've got here s minus 2 squared plus 1. So that matches up with these last two, s minus 2 squared plus 1. Does everyone see that? Okay, so it's going to be these two. Now the only issue left is this s plus alpha here. For the cos term, we have s plus alpha at the bottom, s plus alpha at the top. If we look here, at the bottom, for that middle term, we've got s minus 2, but the top is just s. Okay, that's a problem. So we're going to fix that by subtracting 2 and then adding 2. Now the top part looks the same as the bottom part if we just include these brackets here. Yeah. Does everyone see that? We just want to make the top part look like the bottom part there. And that's it. We can split this up and then go back. So the first one, this 1 over s, we said goes to 1. So we can write that down. Plus. And then the 1 over s, s squared here, sorry. We said that goes to t. So it will be 1 over 5t. Okay. Then this one over here with the s minus 2 at the top and the bottom, we go back to the table. That's going to be this over here with the cos. Okay, the alpha was minus 2 and the omega was 1. So we just write that in. Right, the alpha is 2 because it's the s minus 2. And then the omega is 1, so it's just cos of t. Plus, and then the last one, we can just combine with this plus 2 here and this over here. And then that will be the one with sine. this one over here with the omega at the top. Right? You see there's this omega here and omega squared. There's the one here and the one here. That's the omega. Okay, so that will be plus 13 over 25. E to the 2t sine t. Okay. Any questions for this example? Again, this won't be directly tested in the test and the exams. So I won't say use the Laplace transform to solve it. I leave it up to you to figure out what method you want to use. So if it's the second order constant coefficient, you can use the method we did on Tuesday. You can use this method. Later on in the semester, we'll go through 2 more methods. You can pick whichever one you want. Yeah. But next year, you will be asked to do this specifically. The question will be, solve this using the Laplace transform. You have to do it this way. Okay. So this year, you're a little bit lucky. Next year, not so much. All right. Any questions for this? Okay. Okay. Let me just give you one more homework problem to try. Okay, so for this one, please go through all of the steps again to try and solve it. Then do it again using what we did on Tuesday, and then compare your answers. Okay, so we've got 2y double prime plus 5y prime minus 7y is equal to 3t squared. Okay, so that gives you the equation. Now, for this to be an initial value problem, we need 2 initial conditions. Let's make things easy for you. So we'll have y of 0 is 0, y prime of 0 is also 0. Okay, makes it a bit easier. If those are non-zero, it just gives you more terms for the right-hand side. Yeah. So homework, please try this with the Laplace transform way, the 3 steps we just did, and then the way we did on Tuesday. Okay. Any questions before we go? You're good? Okay. And then please remember the test coming up soon on the 11th. Okay. Class test 3 on the 11th. So you got a week and a little bit. Okay. Any questions before we go? Yeah. Oh, yeah, the quiz. So the MCQ part of the quiz will be on what we did on Tuesday. So I'll give you the differential equation like this. Over here. Okay, something like that. And then there's 3 or 4 options. You need to pick which one. Okay, so you know is it case 1, case 2, case 3? Okay, so that will be for the MCQ part. And then the written part will be what we did here for the inhomogeneous. Like this one. Okay, so that will be for the written part. So finding the characteristic solution, finding the particular solution. Okay, that will be 10 marks. All right, any other questions? Okay, so MCQ, that will be on the case 1, case 2, case 3 stuff. And then the written part will be one of these inhomogeneous equations. I suggest you do it the way we did on Tuesday. If you want to try it out with the Laplace transform as well, that's fine. You can get 20 out of 10 if you want. But I suggest you do it using the Tuesday method. Okay, for the quiz. Right, anything else? Well, good. Yeah.